Okay, so I think we are live again. It's a pleasure for me to introduce our next speaker, which is Alex Grilo. I hope I pronounced this correctly, Alex, from CWI and QSoft in Amsterdam. And he's presenting on the QMA-hardness of consistency of local density matrices with applications to quantum zero knowledge. The stage is yours.
So yeah, thanks, Peter. And I'll present this joint work with Anne Broadbent, and just update, like now I'm at Leipzig and Sorbonne University and at CNRS. And as you can see in the title, one of the main subjects of our result is about studying the consistency of local density matrices problem. And intuitively, this problem asks if you're given pieces of a quantum state, of a potential quantum state, if there is indeed a global quantum state that is consistent with these pieces. So let's be a bit more formal. The input to this problem, the description of M density matrices on k qubits. So for instance, here it's an example of density matrices. So we have row 1 up to row M, and they have a non-trivial intersection. And here I just depict it in 1D for simplicity, but it could, like these density matrices could sit on any subset of qubits of a bigger n-qubit state. And then we want to decide if, given these density matrices, if there exists a global quantum state psi on n qubits, such that for every I, the reduced density matrix of psi on the qubits corresponding to rho I is actually close to this density matrix rho I. Or on the other hand, for every state psi, there exists always some density matrix rho I, such that the reduced state of psi on the corresponding qubits is far from rho I. Okay, so we want to know if there is this global state that's consistent with all of them. And our goal here, understanding how hard is this problem, how hard is given this density matrices, answer this question. And in order to describe the complexity of this problem more precisely, I'll first give a step back and give a background on complexity theory. And I'd like to start with the celebrated complexity class called NP, which formalizes the notion of deterministic proof verification. And we say that a problem is in NP if you have a polynomial time deterministic algorithm that receives two inputs. First, an instance to the problem, and Y it's a candidate proof as a solution for this problem. And then this polynomial time algorithm should accept or reject Y, like this proof Y for this problem X. And what we want is that for this to be a good proof system is that for all true statements, there exists a proof that makes this verification algorithm accept. And for all false statements, no matter which proof is given, then this verification algorithm should reject. And NP has a central place in classical complexity theory. And given the development of quantum computing, it's natural to understand how quantum could help us proving more statements. And this leads us to the definition of QMA, which stands for Quantum Merlin-Arthur, and it defines the notion of efficient quantum verification. So here we have in QMA, we have two differences. So first, we have a polynomial time quantum verification algorithm that receives still an input to this problem. So the problem is still classical, but now we are also allowed to have a quantum proof. And what we want is that the quantum verification on this instance and the proof should decide to accept or reject this proof, this quantum proof for this problem. And again, what we want is that for true statements that there exists a quantum proof that makes this verification algorithm accept, but now with high probability. And for false statements, no matter which quantum proof is given, this verification algorithm should reject with high probability. Okay, so this is the quantum notion of like the quantum extension of NP. So back to our problem of deciding if these density matrices, they have a global state. They come from a global state. Liu in 2006 showed that this problem is actually in QMA. So he shows that there exists a quantum proof system that allows us to distinguish these two cases. And in addition to that, Liu also showed some partial results on QMA hardness, meaning that every problem in QMA could be actually reduced to this type of problems. Since then, it was conjectured that this problem was actually QMA hard, but and the main contribution of our work is proving that this is indeed the case. So the consistency of local density matrices is indeed QMA hard. And on top of this proof, what we also show that this QMA hardness also allows us to have some applications to quantum complexity theory and quantum cryptography. And for the rest of this talk, first I'll give some a sketch of proof of how to prove this QMA hardness of CLDM, and then I'll give an intuition of how to prove new quantum zero knowledge protocols for QMA. So let's start with the proof of QMA hardness. And the main tool that we need for proving this QMA hardness is the notion of simulatable codes, which was defined in my joint work with Slofstra and Yuen. And here I'll define the simulatable codes by example. And I'd like to first start with a warm-up on it. And this warm-up is just a STEAM code. So if you consider the STEAM code that maps the logical qubit 0 into this 7-qubit state, and this qubit 1 into this second qubit, this second 7-qubit state. One nice property of this code is that for every possible qubit that's encoded under the STEAM code, if I give you two positions of a code word, when you consider the reduced density matrix of the encoding of rho on these two qubits, you have the identity. So you can just check by inspection that when you check two qubits from this code word, you have the identity. So in particular, this implies that you have very efficient algorithm that receives I and j, and it outputs the classical description of this density matrix, right? Because this algorithm could just output identity. But the problem is that this fails when you, sorry. And more importantly, this, one nice property of this algorithm is that it is independent of this encoded state, so independent of rho. But the problem with the STEAM code is that when you go, instead of having two positions, if you're given three positions, then you don't have this anymore, because then the encoded state is different for different coders. So you can check it just by inspection. Also for 0 and 1, if you have the density matrix, the reduced state on the three first qubits, they are different if you have the encoding of 0 and 1 because of the distance of the code. So the idea of having the simulatability of codes is giving a step further that, and showing that actually if you consider instead of the simple STEAM code, but the k-fold concatenated STEAM code, then you can simulate bigger and bigger density matrices. So in particular, I show that if you have a log S fold concatenated STEAM code, then you can simulate any reduced density matrix on S qubits of a code word without knowing the encoded state. Okay, and that's what I just said. But there's an interesting thing with simulatable codes is that we not only can simulate the code words. We have a classical algorithm that simulates that outputs the reduced density matrix of code words, but it also we're also able to efficiently compute the reduced density matrices on partial computation on code words. So for example, we know that the STEAM code or the concatenated seed code accepts transversal Cliffords. So if you start with encoding of row and you apply Hadamard's on each qubit of this encoding, then you have the encoding of Hadamard applied to these reduced asymmetrics. And what we're able to show is that we not only can compute the reduced asymmetrics on S qubits for encoding of row or encoding of H row, but for every intermediate step of this computation, it's still we're still able to compute the reduced asymmetrics. And this not only works with transversal gates, but also with gadgets that would allow us go beyond Clifford. So for example, if you have the T magic states and you have the T gadget that allows you to compute the T gate on this encoded psi, then we also show that for every intermediate step of this computation, we can also compute classically the reduced asymmetrices on a subset of the qubits of the intermediate step. And this wraps up the first tool that we need in order to prove our result. And the second tool is the celebrated Feynman-Kitaev construction, or the circuit to Hamiltonian construction. And in this construction, we start with this verification circuit, which we decompose in, for instance, in Clifford plus T gates. And this verification, like this QMA verification, it also receives as input some quantum proofs phi, and it also has some auxiliary input qubits started on zeros. And what Kitaev showed is that given this verification algorithm and this input, we can have a reduction to, just given this verification, you have a reduction to a 5 local Hamiltonian HV, such that first, if the verification algorithm accepts with high probability on this initial state, then we have that the history state of the computation has low energy in respect to HV.
Alex?
Yes?
I have a question here on Slack. I tried to not ask every question right away and said, okay, the question will only be asked if at least 10 people vote for it, so to say, okay. Give it a thumbs up. Okay. So this is a question by Sevak Garibian, who was a bit confused. He says, Yi Kai showed QMA hardness of consistency under Turing reductions, and he thought your work improves this to many one reduction.
So okay. I didn't want to get into this detail. So when I said partial result, because usually in complexity theory, when we talk about the reductions and QMA or NP completeness or everything, we have Karp reductions. So what Ikai shows is that CLDM is QMA-hard under Turing reductions, and that's what I said by partial results. I didn't want to get to the level details, and then with our result to show that CLDM is indeed QMA-hard under Karp reductions, which is the standard type of reductions in complexity theory.
Thank you, Alex.
Can I continue or?
Yes, please continue. Okay. Yeah, we also have the roundtables afterwards.
Okay. So as I was saying, if you have a QMA verification where you have a circuit V, and it is a yes instance, so V accepts with high probability, then the history state of this computation has low energy in respect to the Hamiltonian. And by history state, I mean that the superposition of snapshots of this computation. So meaning that I have a uniform superposition over a timestamp T that goes from the first gate up to the last gate. And then you have the initial state. On the initial state, you apply T, all the first T gates on the computation. And I call this the history state of the computation. And what Kita also showed is that V accepts the initial state with low probability for all states phi. Then actually all states have high energy in respect to this Hamiltonian HV. So ideally, what we'd like to have is that would be to show that you can compute. We have a classical algorithm that computes the reduced matrices of the history state, but unfortunately, we don't know how to do that. And our goal here is to tweak this verification system in a way that whenever you consider its history state, then there is a classical algorithm that will allow us to compute the reduced matrices. And the way that we tweak this verification algorithm is by putting in there these locally simulatable codes. So as I said, we had this verification algorithm that received the proof phi. And now we consider a variant of the circuit that we call V prime, where instead of receiving phi on the clear, it will receive the encoding of the state phi. And this verification of V prime first checks if this state is correctly encoded. Then it creates the encoded versions of auxiliary bit 0 and magic state t. And with this encoded of phi and 0 and t's, the verification algorithm V prime can perform V, but on the encoded state. So it can apply Clifford transversally and T gates via magic states. Via T gadgets. And at the end of this computation, this verification V prime, it has the encoded version of the output. And so V prime can just decode this output, measure it, and decide to accept or reject. Okay, yes?
Alex, I have another question that got past the 10 thumbs vote. It's by Barbara Terhal. And she was asking, how does the S-simulatable, or how does S-simulatability relate to the distance of a code?
Oh, yeah. So in my paper with N, we show that the S-simulatability is a bit smaller than the distance of the code, but they're almost the same thing.
Okay, thank you.
So this is the main idea of how to divide V prime, but for technical reasons, we need a bit more complicated. So instead of having the encoding of phi on the clear, we added what we do is have the encoding of the quantum one-time pad of the state, and we also give them along with the one-time pad keys. And before running this verification V, since the verifier V prime has the one-time pad keys and the one-time pad state, it can just undo the one-time pad and perform the computation by itself. And this is crucial for the proof, and I'd like to highlight here that it's not the main thing. It's not the key point for our result. And given this verification V prime, what we're able to show is that using these properties of locally simulatable codes, we can show that there exists this classical simulator that can compute in polynomial time any density matrix of the history state of V prime on up to 5 qubits. And moreover, we show that when you have this simulator that computes these density matrices, we have a global state consistent with them if and only if we have an yes instance of the QMA. So the idea is that this simulator will behave as the reduction from any problem in QMA to CLDM. And the second property shows us that you map yes instance of CLDM of QMA of the QMA problem to yes instance of CLDM and vice versa. And I'd like just to give a sketch of the proof. So we show this previous theorem that I mentioned by showing that we can simulate, we can compute the 5 qubit reduced density matrix of every snapshot of the computation. then we show that that not only you can do it for snapshots of computations, but superpositions of small intervals of the computation. So instead of having the whole history state, you have just superposition of a small interval of this QMA verification. And finally, we show that given that you can compute intervals, when you consider the whole history state, and since you're tracing out a lot of the clock qubits, then the remaining part is just a mixture of small intervals, and then you can reduce to 0.2 and show that you can compute the reduced matrix of the whole history state. Okay, and this is the overview of the proof, and now I'd like to spend a few minutes describing the applications of our quantum zero knowledge. But first, I want to define what an interactive proof system and quantum zero knowledge means. So when I said about QMA, you have just a prover that sends a single proof to this verifier who decides to accept or reject. But with interactive proof system, we can consider the setting where the verifier and the prover exchange messages back and forth. And again, what we want is that for true statements, V, after interacting with P, accepts with high probability. And for false statements, V should reject with high probability. So this is an interactive proof system, but for cryptography, we also want, usually want a third property that's called zero knowledge. And this is this means that if X is a true statement, then V should not learn anything else from the fact that X is a yes instance. And this is a very non-intuitive definition, but let me try to describe it. So the idea is that V, let me try to define it. So the idea is that V, now we consider V to be malicious and trying to learn as much as she can from the prover. And we can assume that this malicious verifier output an arbitrary quantum state row. And in order to show that this problem, that this verification is not learning anything, we require that you have a simulator that runs in polynomial time and does not talk to the prover and outputs some quantum state sigma, such that no efficient algorithm can distinguish rho from sigma. Okay, so the idea here is that this simulator that has no access to the prover can somehow output some quantum state sigma that is indistinguishable from rho. And zero knowledge is very important in classical cryptography because it's used in several settings such as Bitcoin and so on. So our goal here is trying to understand this type of protocols also in the quantum setting. So in particular, there has been a recent effort in devising this type of zero knowledge protocols for QMA. And we have seen several proposals that show the quantum zero knowledge protocols for QMA. But one downside of them is that they are a bit complicated and they need multiple rounds. So in this work, by showing QMA-hardness of CLDM, we can finally show simpler quantum zero knowledge protocols for QMA. And I'd like just to describe one of these simple protocols that we propose. And I think I'm running out of time, so I'll try to explain this zero knowledge protocol directly. So the idea is that in this protocol, that the verifier it has a description of density matrices, and we wanted a prover to be able to show that there exists a global state consistent with them, but without the verifier learning this global quantum state. So the idea is that the prover has copies of this consistent of this global quantum state psi, and instead of sending them in the clear to the verifier, what the prover could do is one-time pad them and keep the one-time pad keys of this encoded state. And instead of sending the one-time pad keys in the clear, it puts them on a safe. And safes in cryptography are called bit commitments. The prover can then send the encrypted state along with the safes to this verifier, but keeping the code to open the safes. The verifier then asks the goal of the verifier is to test if these states they are consistent with the ith density matrix that's picked uniformly at random. So the verifier asks the prover to open all the safes corresponding to the qubits of I. So the prover can send back the codes that open the safes, and the verifier can retrieve the one-type keys, decrypt only the qubits corresponding to the density matrix rho I, and then using the protocol, the QMA protocol by Liu, the verifier can then check if this reduced density matrix is indeed consistent with rho I. So yeah, I don't have too much time to say, but this problem is complete, meaning that if there exists a global quantum state, then the verifier the prover can convince the verifier. If there is no global state, we can show that no matter what the prover does, the prover cannot make this verifier accept. And finally, what's more interesting, this protocol is zero knowledge. And intuitively, you can see that because the only unencrypted part of the state psi that verifier sees is a reduced matrix that the verifier has the description. So he's not seeing any quantum state whose description he does not have. And of course, you have to prove zero knowledge more formally by providing a simulator, but I'll skip it from now. And I'd like just to finish with some open questions. So the first one is we showed that CLDM is hard for when you consider 5-qubit density matrices. So it's still open. Okay, you have these QMA-hardness under Turing reductions, but we don't know if there are also QMA-hard with Karp reductions when the density matrices have size 2, 3, and 4. Secondly, we don't know what's the complexity of approximating CLDM. So we have seen this quantum max cut type of approximations. So can these techniques also be used to CLDM? And finally, I didn't have too much time to talk about it, but one open question is having more efficient quantum zero knowledge protocols for QMA. And with that, I'd like to finish. Thank you.
Yeah, many thanks, Alex. We had quite some interesting questions and also discussions in the Slack channel during your talk. I hope it will be a very lively discussion at the roundtables. So yeah, let's thank Alex again. I can clap my hands here live, but the others, I don't know, can use these the other features. So many thanks. And yeah, I think I don't know. I can probably not really close the session technically, but yeah, let's please all go to the roundtables.
So okay, now we go to roundtable. Okay.
Yes. Bye.
Bye.